That's good. Okay. Hello and welcome everybody right up to this first round of talks right after the keynote. There are still some people streaming in, I see, which is good, but it gets a little bit, gets a little bit cozy. Maybe there are a few more seats left in the front. Okay, I think we can start. Hello and welcome everyone again from my side. I would like to invite you in this next 45 or so minutes on a journey during which we are going to discuss a stateful and reactive stream processing application, and we are doing that without relying on any kind of conventional database. The subtitle of this talk is actually giving away the technology focus that I have chosen for this session. Namely, we are looking into Apache Kafka, especially Kafka streams, and we will integrate with Spring Boot 2.0 for all the reactive goodness that there is to this WebAPI that we are also seeing in action. But before starting and diving into the topics, let me briefly introduce myself so that you have at least the first rough idea about who is talking to you today. So my name is Hans-Peter Grahsl, and I am currently working and living in Graz in Austria. I'm, from a job perspective, mostly in the role of a technical trainer, and I'm focusing on Java-based web development, if you want. And I'm working with Netconomy, where we are building large e-commerce solutions for our customers, basically worldwide. And besides that, I'm doing that part-time there. Besides that, I'm working as an independent consultant and engineer, where I help clients to build data architectures, either on-premise ones or cloud-based ones using modern technology stacks. And time permitting, I'm also teaching as an associate lecturer at the University of Applied Sciences, also in Graz. And sometimes I'm speaking at conferences, so I'm doing that probably not that regular like a bunch of other well-known guys here, but still, this is why I'm here today. So before diving into the topic, let's take a brief look about some of the aspects and challenges that we may face when we are working in the context of data architectures these days. I think we can safely agree that we have to deal with basically a rising number of applications that are producing any kind of data and consuming data from other services found in the landscape. But I think more important than the sheer number of applications or services that we have to deal with is the fact that we need to integrate with ever more different kinds of data sources and data sinks. And this means that we as developers or architects, we have to basically operate in heterogeneous environments on a daily basis in the wild. And this is everything but easy, I would argue. And the problem can arise that when you try to meet all of these requirements with traditional technologies, that you may reach a point where you start to struggle when you were sticking to doing the things like you always did them in the past. And the effects of that can lead to a giant mess, at least from an architecture perspective. And the problem can be that you realize that your system starts to rely on very tight coupling between any kind of different services that you are operating in your landscape. And the good thing about it is that it doesn't necessarily have to be like that, right? There are alternative ways, and sometimes it makes sense that we look at what other technology stacks may offer. So instead of sticking to what we always did, let's try out something new. And one way to approach the challenges that we can face in today's data architectures is to leverage, for example, Apache Kafka, which helps us hopefully to at least remedy some of the major pain points and also to some degree avoid some of the undesired effects that we or that we may face when we are building such systems. So as soon as you enter the world of Apache Kafka, I would argue you are more or less these days immediately confronted with the fact that Apache Kafka is deemed as a so-called streaming platform, right? And at the same time, you might wonder, and I would say legitimately, what the heck is a streaming platform, right? What is this anyway? And I hope that this session at least helps or contributes to a first understanding about what you can expect from a streaming platform in general, and what Apache Kafka offers in particular in that regard. So I think let's start this discussion with looking what Apache Kafka became famous for. And when you take a look, it all started several years ago, and Kafka was very popular back in the days already as a simple message broker, right? but in fact it offers much more these days, as we will see during the course of this session. So first, just to name a few key aspects, we can use Kafka, of course, to publish any kind of data. So our services in our landscape can publish data to Kafka, Kafka topics, and we can then have consumers subscribe to this data and basically work with this data in any way. Other than that, we can also use Kafka, depending on the use case, for temporary storage of messages, but also for a permanent storage. So this means that you can decide very precisely about data retention policies and define how long you want to keep the data that you publish to Kafka. And the third thing, and this is also important because it's the main focus of this session, is that Kafka allows us to do stream processing basically on all the data that is flowing through Apache Kafka. And we can do that with very low latencies, as we will see later. And besides these key capabilities, we can do all of these things with Apache Kafka in a fault-tolerant and highly scalable way. So even if some of you may not have particular scaling needs, right, because typically some systems start out pretty small, then you can still, from the very first day, guarantee or rely basically on Kafka's guarantees when it comes to high availability and resiliency when you run a broker of multiple so-called a cluster of multiple brokers, sorry. And let's take a look, because as developers, we are often interested from the very beginning, how can we interact with any kind of technology stack, right? Let's take a brief look at what we are offered API-wise from Apache Kafka. So first, there is, of course, an API which allows us to publish data, so the producer API. And we can send literally any data that we would like to Apache Kafka. It's not at all opinionated about what you throw at it. At the end of the day, what it does is it happily stores sequences of bytes, okay? And any kind of message structure that you want for your records that you publish to Kafka is left to a mechanism using deserializers and serializers for these sequences of bytes that you want to store. So, for example, this lets you conveniently work with JSON or Avro encoded data that you want to use for your services. Then there is, of course, the consumer API, the other side of things, where we then can process all the data that we have sent to Apache Kafka. And we have a lot of freedom how we want to process this data. So Kafka is very flexible in that sense as well. So you can decide how you process this data, meaning you cannot only, for example, read messages once, you can read them multiple times if you want. You can go always back in time and replay messages if you would need that. Another nice property of the consumer API is that you can define a thing called a consumer group. So this means that you can basically have multiple applications consume one and the same topic, and they distribute the workload among each other. Also a very nice property. Again, not only for scaling needs, but if one of these consumer instances goes down, the other will take over the work of the instance that vanished. So also here you get essentially both things baked into the API, resiliency for the one part, but scalability for the other part. And both these things, the producer and consumer API, are more or less available in all popular programming languages. This means I would be really surprised if you do not find an implementation for Kafka producer and consumer API for a popular language of your choice. Then the third API I want to briefly touch upon is the Connect API. And what it allows us to do is it's particularly helpful when we want to build data integration pipelines. By means of Kafka Connect, we can very easily connect more or less any kind of data source with any data sink, and we can put Kafka in between as the decoupling element, if you want, as the broker that handles all this traffic. And again, this is of course in a resilient and scalable way. When I'm talking about any data source and any data sink, this of course implies that there is a ready-made Kafka Connect implementation available for the data stores you want to integrate with. But also in that regard, there are already plenty of ready-made connectors available. You just download them, you register them for your installation, and you are ready to go. We will see one such connector instance in action during the demo. Then there is the Streams API, and as the name implies, we can do stream processing on top of any data that is written to Kafka or that flows through Kafka. So it doesn't really matter where the data originates from. It can come from the producer API, it can come from the connect API. Any data that is there and that we are writing to Kafka can be processed in a streaming fashion. And the Streams API is extremely nice, I would say, from a developer's perspective, because it allows us to do a library-only approach for stream processing. And what's meant with that is that we can simply integrate one more dependency to our project, and then decide how we want to build this application, how we want to deploy it, and where we want to run it. The nice property, of course, is when we can do it like that, that we do not need to rely on any kind of additional external stream processing frameworks, and some are listed here. You may have heard about Apache Spark or Storm or Flink, and there are plenty of others in the open source landscape of stream processors when you look at that. So no need to necessarily rely on any of these in addition. You can simply write streaming applications by including a dependency and start to code right away. When it comes to writing this code, we have basically two broad possibilities to write our code. One is the processor API, a low-level approach, if you want, for stream processing. So in using the processor API, you can do more or less arbitrary things, whatever you would need. So for very specific use cases, you would want to use most likely the processor API, but it has definitely a learning curve to it, which is much higher than for the other API that you are offered, namely the K-Streams API, which gives us a really nice DSL to define data flows, right? And there are ready-made operators that you would often need, some of which we are going to see also during the demo. And the nice property is also it has a fluent API. It's very concise, so compact code that you get out of it. I would say it's the better way to start your first try and use of K-Streams API than going to the processor API. So stick to Streams DSL as long as you can, as long as it satisfies your needs, and only then if you find, okay, there is no ready-made operator for what I want to do, take a look at the processor API in a second step. Of course, we get also deliverable guarantees that we can configure. Depending on the use case and how important our data is, we can decide if we want to have Kafka to operate in an at most once fashion, in an at least once fashion, or in an exactly once fashion. And again, I think the huge benefit here is that we can focus as developers on what we hopefully can do best. We can write applications, okay? And we do not need to deal with yet another external additional framework or manage yet another cluster. No need to operate any additional infrastructure to what you already have when you are using Kafka. I would argue that there is one specific, as I would put it, non-functional shortcoming to Kafka Streams. It's the fact that that you have to have developer skills. So either you use the Scala API or the Java API for K-Streams. Both are by now available. But some folks just don't have these development skills. And for exactly this reason, there is another alternative to the K-Streams API, namely KSQL. And besides that, it also gives even developers a real productivity boost. It liberates stream processing for non-developer folks. So everyone basically can do stream processing based on KSQL. And what this is explained very easily. So this is the SQL streaming engine for Apache Kafka, and it gives us what we actually expect when we hear about something that is SQL-like. We get powerful operators to join data, to aggregate data, to filter data, to even do window-based analysis, and so on. And because of that, it has an ultra-low entry barrier. So you can leverage any prior SQL knowledge and start to define stream processing topologies by means of SQL statements only. And it is not like for some other frameworks that you need to embed these SQL statements into a Java code or into a Scala code. You can literally just write statement after statement after statement into a file and have the so-called KSQL server pick it up. And what it then does, it builds under the covers a K-Streams application that is run then like a K-Streams application that would have been implemented in Java. So again, no coding required, very easy to get started with. And if you face any situation where the out-of-the-box features are not enough for your use case, you can easily extend it. Of course, when you want to extend it and write your own user-defined functions or user-defined aggregate functions, you then need, of course, to have coding skills again, like for any other framework where you could do that in a similar way. So what you see here is basically a generic depiction or a summary what we have just briefly discussed, where all the things come together that Kafka allows us to do. And I think when we take a look again at all the options, the integration points, the different APIs, the core characteristics, main features of Apache Kafka, it becomes apparent that Kafka can really act as a platform for streaming data. It has been conceived from the ground up as a platform for data in motion. And exactly in that sense, Kafka has the potential to become, if you want, your central nervous system of all your data flows that are happening in your enterprise and powering your businesses. I think with that slide, I want to already switch over to the example-driven part of this session. And well, for that, of course, we need an example, right? And while I was doing this particular slide during the preparation of this talk, it suddenly struck me. And I realized one fact, namely that emojis are everywhere, right? So we are using them when texting friends and families. We are, of course, using emojis when we comment on social media platforms like Twitter. People made even full feature films starring a bunch of well-known emojis. And to top this off, I recently heard rumors that even IoT devices started to express their feelings from in the field by means of, well, you guessed it, emojis, right? I'm just kidding, of course, here, but the actual intention was that I wanted to have a very simple and easy to follow example, which is colorful and memorable, and one which doesn't rely on, you know, any kind of simulated, randomly generated fake data, but uses a real-world data source. And for that reason, we are going to see how we can build a near real-time emoji tracking app built on everything that Apache Kafka has to offer. So we will integrate with Twitter Streams API for that reason, and based on the public tweets that are flowing into our system, we will build an application that allows us to count essentially how often we have spotted one of the emojis within any tweets that are coming into our system. Okay, so a very simple use case, of course. How would you build this? And I decided to break this up into 4 different steps, and each of these steps basically deals with one particular aspect of how to build stateful and reactive stream processing applications. So step 1, of course, we need to find a way to get the data that we need, the data that we want to process in a streaming fashion. And we will integrate, as I said, with Kafka Connect's API to read tweets off from Twitter as we are speaking. Second step will be about processing this data in a streaming fashion. Okay, we want to extract any occurrences of emojis out of this stream of tweets, and we want to group them and count them. And for the sake of this example, it's also helpful if we find a way to maintain a list of the most popular ones, so that we can, what we have seen on the dashboard, that we can somehow show them with their respective counters and see the most popular ones that we have or based on the values that we calculated since we started processing our data. Then we want to see how we can add a querying layer on top of what our stream processing application does, so that we can, for example, query for a single emoji count, or we can query for all the emoji counts that are happening, depending what we would need from a client perspective. And the fourth and last step actually is to find a way to do some kind of near real-time notification, so that we can provide a stream of all the changes that are happening in our streams application to clients, and they can consume these streams in near real time. So let's do this and look at all of these steps in a bit more detail, and we also see hopefully working demos during the rest of this session for each of these 4 steps. But remember that where we are going, we of course don't need any databases, right? So step 1 it is, okay, ingesting tweets. And for that, we are using Kafka Connect, the so-called Kafka Connect source connector. You can find this connector on it's a community connector. You can find it on GitHub. It was written by a guy called Jeremy Kastenborder. And like for any other connector, basically all we need to do is configure it properly. And after having a configuration, which is a simple JSON file, we can interact with Kafka Connect's REST API and manage connector instances. Okay, we can create, of course, new connectors to start data flows. We can pause them anytime to stop their work. We can resume them later on if we want to need that. We can delete them completely, and of course we can check the status of such connector instances at any time. This is how a configuration could look like for the example in question. So besides defining a name and the implementing class of the connector, you also define what kind of data it is that you want to process. And in this case, we get back from Twitter JSON data. So that's why we will later define a JSON conversion. But first we tell the connector where to store the data it reads off of Twitter. So we specify basically the Kafka topic by name where we want to write this data to. And then comes this configuration of how should these key value pairs of records be converted. And in this case, again, we are dealing with JSON data. It can be a different format like Avro if you would use that. I think you want to see this in action. So let me move out of the slides for a second. Just let me go on the command line and check if my local instance of the Kafka services is running. I'm using the Confluent platform, by the way, which is, I think, the most convenient way to get started. You get a CLI that cares about bringing up all the needed services on your local machine. Of course, if you prefer a Dockerized environment, there are Docker containers as well. I just decided to stick to this Confluent platform for simplicity reasons. So, and then what we do is we post a configuration to the REST endpoint of Kafka Connect. Okay, and what you see here is the whole configuration fragment, including some Twitter secrets. So please forget them after seeing them. So I sent this and post this to the connector. Oh, and it says it already exists. Let me delete it first. So there was another connector obviously running during my tests before the talk. So let me do that again. So now we have a connector instance up and running. This is good. So let's check if this connector instance already does something. For that, I switch to the command line, and I will use the built-in console consumer to consume from this topic, and we see the data, hopefully, that gets ingested currently in the background, flying across my screen in a few moments. There it is. This is the live data that comes in for some certain filter keywords that we defined in the config, and this is live data coming from Twitter as we speak. So obviously the data ingestion part already works. Let me stop that here. So it happily runs and saves data to Kafka in the background while we continue. So let me go back to my slides. Well, no coding, right? Just by configuration, we managed to ingest data from a source, in this case, Twitter. And you can do that with different data sources. As I said, there are ready-made source connectors, of course, for other use cases as well that you can just use by configuration. So this brings us already to step 2, okay? So this stream processing of the tweet stream that is stored to Kafka in the background. And we are using and discussing this based on the high-level streams DSL. What we want to do is we want to extract any emojis that may or may not be in the tweets, and we want to group them and count them. And as I said earlier, we also want to maintain a list of the most popular ones. And we will see that this very specific and small example is only a few lines of Java to do that using the streams DSL. So how does it work? Okay, it all starts with raw data, tweets like this that may or may not contain such emojis. In this case, we have 3 different ones and in total 5. And what the program then does is it does a bunch of operations that are chained together and form a stream processing topology to process this data, okay? And the first aspect will be that we find a way that we can, from this raw input, extract a list of potentially contained emojis, okay? And I'm of course using an emoji library for Java for that, because trust me, you don't want to do that manually or on your own. parsing emojis from text, I mean, sounds maybe easy at first thought, but it's pretty challenging. So I would also recommend that you use a library for that. Having this list, and again, we are only looking at a single tweet, right? The same then happens for basically all the tweets that are flying into our system. And after that, we flatten this list, so we essentially explode the list so that we get separate key value pairs for each and every entry that was found in the list. Next step is that we then switch the key value pair. Data in Kafka is always processed in terms of key value pairs. So we switch so that our values become the new keys. We do that for the reason that we can then finally group and count these data by key. And what results of this is a so-called K-table. And again, for this single tweet, it would look like this, that we found the Swiss flag 2 times, the mountain icon 1 time, and the cheese icon 2 times. And the nice thing is that while the program is running in the background, this K-table gets continuously updated. Right? Every time it spots a corresponding emoji code, it will increment counters on the right side. This is what basically happens. And all of what we just discussed has a very natural, actually one-to-one mapping to the K-streams DSL. So this is the very core of the code that's needed to do the stream processing by means of K-streams. We first transform this data so that out of a full tweet, we extract only by means of emoji utils a list of emojis. In the next step, we flat map these values, so a normal flat map operation that you would be used to from any other either stream processing framework or any other functional library or the Streams API. So conceptually very similar what it does. Then we make this swap of values and keys so that then our emoji codes become the new keys. And finally, we say we want to group by key and we want to use a simple count function as an aggregate function. You can, of course, use different pre-built aggregate functions, and in general, you can do basically arbitrary stateful computation as well by writing your own aggregate functions. Again, let's see how this behaves in action. And for that, let me bring up a Spring Boot instance of a K-Streams application on my command line. And hopefully after a few moments, we will see on the debug log a lot of new codes flying across the screen. This is it. So we see every time we find and find and spot any emoji codes, that the counters are increased accordingly, right? And this happens in the background as new data arrives. Of course, we can, just to show you, we can, for example, pause the data ingestion by sending a request to the Connect API. And what this then causes is that my application stops, right? It processed all the data that it has seen so far, and it waits now for new data to come. So if I start or trigger the data input process again, the connector, let's resume the connector, then we see and hopefully see that the application continues to process new data as new tweets arrive. So far, so good, right? We have seen that we can build this using the K-Streams API, but the problem is, I would argue, that we cannot yet access what we have seen on the debug log, right? It's as if the state that is mutated and updated all the time in the background is locked inside the application. And for that reason, we need to find a way to add a query layer to all of this. And thanks to Kafka Streams, 2 concepts are there which help us to build that with relative ease, I would argue. So first of all, every time you do stateful computation, Kafka Streams maintains so-called state stores, and they are local to the application. So this is not data that is stored in Kafka, but as a state store in the application. There are different implementations how such state stores can or how such state stores are working. One is baked by RocksDB, a famous embeddable key value store, I think developed at Facebook, and the other is, for example, an in-memory state store, and this is what I'm using here, right? So there is nothing of the state is persisted so far. And then in addition to these state stores, it gives us interactive queries. This means that we can access these state stores and do very simple key-based lookups against the state that the application manages. And Kafka Streams does all the heavy lifting for us and provides us the metadata that we would need in order to build such a query layer. And everything else is then left for developers. So you decide how you want to build your RPC integration API on top of Kafka Streams. And I decided for convenience reasons to use the reactive web stack of Spring Boot 2.0 because it's very simple to work with, and you will see that it's not really difficult to get it going. Pretty straightforward what we need to do. So there is a REST controller, obviously, which allows us to query for different things. Okay, we define the routes and the get mappings for that. A traditional Spring REST controller, annotation driven, like you would have seen in other examples as well. So nothing special here. Also, when we look at the two of the controller's methods, they are pretty familiar, right? You have a get mapping, and you then what you see here is that the controller method just delegates to a service. So we will come to the service a bit later. What may be a bit unfamiliar to some of you are the return types, namely mono and flux of something, right? And if you haven't seen the reactive web stack of Spring, this looks a bit weird, but it's not that hard to understand. Actually, if you have maybe seen any other reactive libraries in the past, like any of the RX-based families of frameworks or libraries, then you have an easy time, I would say, to understand how to work with these reactive data types, mono and flux. Mono and flux are defined by Project Reactor, and this Project Reactor is used inside Spring Boot and Spring 5 actually to build the reactive web stack of Spring on top of Reactor. Flux, for example, works conceptually very similar to what you would be used to when working with observables in RX Java, for example. And the service does all the work here. So let's see what the service actually does, because obviously in the service there happens this interaction of querying the state stores. And the way this works is that you first start and ask k-streams about the metadata for a specific state store. And you define the state store by giving it a name. And then you hand it the key in question, right? In our case, the key is, for the example, an emoji code. And then Kafka Streams tells us the metadata about the state store and the emoji code. We do that because of the fact that we need to know which application instance is actually managing the state. In general, I'm just running here a single application. You can easily scale out and start multiple applications, and then they will split the work again. And then parts of the state that you are mutating are found on one instance, and parts are on another instance. And this basically tells us where we can find on which application instance we find the corresponding state. And if it's the application instance that received the REST query, so meaning the state is locally available, we can simply ask k-streams to give us the state store that we can then just query by a simple get call with the key in question. And we can then return the counter that is found in the state store for the specific emoji, in this case again because we are reactive as a mono. If it's not the correct application instance that received the query, thanks to HTTP, we can do a very simple redirect. And we redirect the client request just to the correct host that k-streams told us is responsible for the state in question. So very simple stuff. Again, let me show this to you in action. So I will go to the command line. It's processing. So here I will fire a few pre-made curl requests to get back codes for specific emojis only, right? You see here 3 or 4 requests telling me exactly at the point in time I was querying what was the specific count for each of these emoji codes. Okay, and we repeat that. We typically see updated counters 8246 it stayed the same. Is there no, let me see if the data is still flowing. Yes, there was. Yeah, now we have 248, so it took some time until we have seen that. Now we do it again. We see, do all of them again. This was only the last one always, so let me do all of them again. This one. Now we have already 58, 65. So you see the counters are raising as new data arrives. Here it stayed 65, but it will increase again as soon as there is new data. So you would see, you see that now it's 67. You see this is not ideal, right? We have point-in-time queries, but this is definitely not enough if you want to build a live dashboard, right? You would need to literally pull the hell out of your web API, and this is not what you should do in general, right? So for that reason, we are not completely finished yet. We need to, let me come back to the slides once more. So what if I told you there is actually no need for polling, right? We can do better. And the way we can do better is that we try to find a way to be able to push down any state changes to connected clients in near real time. And there is two things to it that we are using to build this. First of all, there is this notion of changelog topics in Kafka. And they are there for a reason. They are there to record inside a separate Kafka topic all the state changes that are happening to your K-tables, for example, and also to your state stores. This is there so that you can lose processing instances and be able to rebuild the state based on these changelog topics. So for resiliency reasons, we have this changelog also stored in Kafka topics. And we will find a way, if we find a way to reactively consume from these changelog topics, we are almost finished, right? The only thing that's then left is to find a way to expose this information to connected clients. In our case, we will have a web application running in the browser that wants to consume these change feeds. And I decided for convenience and for simplicity to just use servers and events for that. But of course, this would work with WebSockets as well. And this reactive consumption of the changelog topic actually is done again with a project that comes from Project Reactor, a project called Reactor Kafka. It allows us to consume from topics and produce to topics with reactive data abstractions on top of. So this is what this project gives us. And based on this Reactor Kafka thing, all we need then is to provide another controller method actually that sends back all the change events. And thanks to Spring Boot, we can easily do that. We just defined a different media type that it should produce and say this data that is pushed over this flux return type should be sent as server-sent events to any connected clients, okay? And again, the service that's used, that the method delegates to, does the heavy lifting, but again, it's only a few lines of code. I will point you to the fully working example then at the end anyway. So it reactively consumes from the changelog topic and exposes these topics as a hot publisher source. So nothing fancy, pretty straightforward. Let's see this in action. And with that, I'm happy that I can share with you finally a live dashboard where we will see then in the application, in the web application, how these codes are updated on the fly in near real time. Okay, so I'm just checking and bringing up the instance here. I will restart it just to be safe. The front-end application is written in Angular in this case. It's an Angular SPA and it uses RxJS. And thanks at this stage to a front-end engineer colleague of mine who quickly put this together. Thanks, Lucas. I'm not a front-end guy, so I'm just using what he built for me. So in order to explain what happens, I will stop the data flow just briefly so that we can see how the program behaves. So I will call the application, and what it does right after starting, it goes out to one WebAPI endpoint and does a point-in-time query of the most popular emojis that are calculated at this point in time. So there we only get back one such result. And immediately afterwards, it subscribes to this changelog stream, which we will see in the left column of the screen. It is now empty because there is just no new data arriving. We have processed everything so far. And then based on the changelog feed, it will do client-side updates of this dashboard in near real time, okay? So if I now resume the data flow again, we will hopefully see in the left column here, new data flowing into the system. And you see that the values get updated here in the middle to reflect any changes to the counters as they are happening on the server-side K-Streams application. We can also do another thing. I mean, this is just there for demo purposes. We can click on any of them and see which of the tweets actually were there to increase the values. Let's take this one. Hopefully nothing insulting comes up, so please don't blame me what people are writing on Twitter. Let's wait for, yeah. Okay, this is pretty neutral, right? We and 3 smileys with tears in eyes, but you get the idea, right? You see essentially which of the tweets were, oh dear, yeah, dog eating money. Yeah, you know, these things are written on Twitter. I'm not blamable for that. But this is basically, this is the dashboard that we wanted to build in the first place, right? And there is no database involved, and I could go now and kill the application, the K-Streams application, run it, and it will be very quickly, because the state is not that large, it will rebuild all the state and continue where it left off. So no database is involved, only in-memory data. And if the application goes down, well, you restart it and the state will be rebuilt from scratch in that case. Okay, I think with that, we can confidently say, I guess, mission accomplished. So we have achieved a pretty nice example, I guess, during this session. We started by defining a data flow based on Kafka Connect without coding. We then managed to do stream processing with Kafka Streams. We built a query layer thanks to Spring Boot 2.0, and we then also managed to get these near real-time notifications pushed down as server-sent events to any client applications. Yeah, we are coming in a second to the questions and answers round. If you want to try that out, the source is already on GitHub. Also, the slides are on Speaker Deck. So feel free to try it out yourself. Yeah, other than that, I think we can more or less switch over to the question and answers round. Thanks a lot for the organizers for giving me the chance to talk here. Thanks a lot that so many of you came. I hope you found it interesting. I wish you a great day and have a nice rest of the conference. And I'm happy to take any questions. Thank you very much.
So you said you don't need the database because you rebuild the state from the beginning each time. Now, if you have a very large data set, you will not do that. You will need to keep some state. Yeah. What would be the strategy?
So first of all, it was not completely right, because in this case, I would rebuild the state from scratch. But these changelog topics, they are organized in a way in Kafka that they typically keep only the latest state for each key in this topic, okay? So instead of reprocessing millions of messages, you only reprocess basically each message for each unique key once, okay? That's one optimization to help with making the rebuild of the state quicker. The next aspect is normally you would never lose your full state. This was an in-memory state. I said you can also decide to configure it that the state is baked locally to the application instance in a RocksDB on the file system, in a RocksDB KV store. And what you can also do is that you can define a setting in Kafka Streams that is called number of standby replicas. And what this means is that it tries to have a replica of a state. And in case one instance goes down and you start another instance, it tries to start the instance where parts of the state are available, because there was a standby replication of the whole state. So ideally, you have the state store not only once on each application, but maybe 2 or 3 times. That's one part for resiliency as well. And if one instance goes down and you have 3 others, you would temporarily only use the state that this one instance managed for a short period of time. And immediately afterwards, the other application instances that are still working will take over the load and try to rebuild this state only that was lost on one instance. So in general, it doesn't take very long, but you are right. The larger the state, the longer it can take to rebuild it.
So this case store, behind the scenes, we have topics that Kafka or K-streams manage itself.
Yes.
For this replication, and everything is done behind the scenes using topics.
Yes. So the topics, the changelog topics, are what is persisted at Kafka. The state stores are persisted locally to the application. They have nothing to do with Kafka. Okay. The state is local to each application instance. Kafka does not know about the state stores. Kafka only knows about the changelog topics. Okay. So these are 2 concepts. One is the application, one is the Kafka cluster.
And the replication between the application instance, K-stream applications, it goes through topics? It uses Kafka?
So the changelog topics themselves are replicated like normal Kafka topics are replicated for fault tolerance reasons. Again, this is independent of the K-streams app. And also the state stores can be replicated to other instances, but not, again, application instances and not Kafka clusters, okay? So these are 2 different concepts. One is the Kafka side of things with changelog topics, and the rest, the state stores, are always local to the applications, okay?
Hello. We've seen a connector to the Twitter consumer API.
Mm-hmm.
Is there any security mechanism built in? Otherwise, we are managing it via REST, and everybody could go to this instance and just tap the connector?
Yes. So first of all, the REST API, of course, allows you to do HTTPS, so to interact with HTTPS, and you can, of course, do authenticated REST requests to the Connect instance. Okay. Maybe this was meant. So yes. Short answer is you can do HTTPS and authentication in order to be able to start new connector instances, to delete them, to pause them, to resume them, right? I was just using plain HTTP here for simplicity reasons. But yes, the REST API supports authentication.
So in general, it's a matter of configuration.
Yes.
Then. Okay, got it.
Yes.
So just to make sure I understood, the default tolerance of your data is given by the fact that there's no central storage by Kafka of the outcome of your streams, but it's offloaded to each application, basically. Or am I confusing things?
So again, there's 2 things. So to one part, all the changes that are happening to the K tables that are updated in the streams application are also written by Kafka streams to these changelog topics. This happens automatically under the covers, right? And by this, all the change or large parts of the state changes, because there it happens how you configure it. You can say you want to really write to the changelog topic every single small change, or you want to write them in an accumulated way. But at the end, they will be persisted in a Kafka topic, which itself is replicated in the cluster. And on the other hand, we have this K-streams mechanism that is only there in K-streams, the state store mechanism, that is only there that we can quickly access the state that is changing in applications by means of this query mechanism. Okay? So because we had, if the state stores local to the application weren't there, we could not easily build a query mechanism, because we would need to build that on our own based on the changelog topics. And this is also what Kafka Streams already gives us and does for us by means of the state store concept.
Thanks.
I have a quick question. Are these state stores, are the changelog topics subscription relative to one single state, or can be, let's say, to multiple states? I mean, maybe...
No. So basically, for each stateful operation that you are using, you get changelog topics, okay?
But can I do something like them shifting between the states?
Shifting between, so actually whenever you do a stateful operation in your K-Streams code, you can decide which state store it should create for you, okay. And you give it a name. And based on this name, you can access this very state store. There can be multiple state stores in a single application, of course, if that was the question, and they work independently from one another. Okay.
Yeah.
So you decide basically whenever you apply a stateful operation in your streams topology, you decide if there should be a state store, how it is called, and if it should be, for example, RocksDB baked or in memory. You can very specifically configure that.
Okay. Thank you.
We are done. Thanks a lot. Enjoy the rest of the day.